Alright, hi y'all. Today we're going to be going over cascading op amps and really just how to, figure out which equation to use. Either you use your inverting amplifier or non-inverting amplifier. So when you're doing these types of op amp questions, when you have multiple op amps, as you can see in this practice problem here, what you want to really do, or at least what I do first, is I ask myself two questions when I'm looking at these, maybe sometimes interesting configurations. My first question is always, do I have negative feedback? If I do, what does that entail? Well, for one, that means you have a virtual short at the inputs of the op amp. What does that mean? Well, that means V plus is equal to V minus. I know in the previous practice problems, or in the previous op amp video I made, I said always for these ideal op amps we have V plus is equal to V minus, but this happens when you have negative feedback. In this class, EC 3355, we will only be dealing with negative feedback, so there's no real problem with what I said before, but I guess for anyone that isn't taking this course specifically, just be careful. If you have positive feedback, it might be different, but for negative feedback specifically, this is true. Also, for ideal op amps, you have no input current. What that means is, in this picture here, you notice that there is zero, these arrows with zeros. These go towards the input of the op amps. That will always be zero. And the second question I always ask is, do I have, or really is, where is the input voltage where's the voltage I'm applying to the op amp? And really what that question is asking you is, do I have inverting or non-inverting? For our class, this will make it very, very easy to pin down exactly what equation you want to use. Now, these op amps might look very, very weird. They might not be in these very easy configurations as you can see here. They might be kind of wonky like in this first problem here. So once I figure out these two questions, I know exactly what equation I'm going to use, whether it be this one or this one. And by the way, for impedances, when we have capacitors, this works the exact same way. You just change it into the phasor domain and convert, a capacitor to 1 over j omega c, or inductors to j omega l. Now, let's get on with this problem here. So, looking here, we have, 3 op amps. That means we have, 3 different, maybe not different, but up to 3 different amplifiers. You could have an inverting and non-inverting, or non-inverting and inverting. You could have non-inverting, inverting, then non-inverting. It really depends on where that voltage is. So let's see. We have what? We have this V1 and V2. Okay, so when you have two different voltages, there are two things you could do. You could either use superposition, which means you let one of the voltages be zero and analyze the response of the circuit using only V1, and then adding that Vout1 to Vout2, meaning you would let V1 be 0 and analyze the response for V2 only. Or another way you could do this is, I guess it is superposition. You could analyze the circuit only here, and then at the same time analyze the circuit here, and then analyze the circuit here with the two different inputs. What I like to do is a little more methodical using superposition. That way you show all of your work. That way you can't get any points off when you skip steps. Of course, if you get the right answer and you know exactly what you're doing, do that. I'm not saying take every single small step. I'm saying that I'm not sure how Dr. Litvinov will grade. He could be grading very meticulously on the steps, like maybe like Dr. Dave. You might want to show all of your steps just in case he takes off points for, how did you get this value? And you're not showing your steps. So that's what I'm going to do here. So these are my 2 questions I ask every single time. And now let's use superposition. So what we're going to do is we're going to let V2 equal 0. Well, what does that mean? Well, that means we have V2 is equal to 0. That means this is ground. Okay, now what does that mean? Well, we have negative feedback here, right? Okay, that means we have a virtual short. That means we have virtual ground, meaning this is also ground. Okay, well then, what does that mean? Well, that also means this node is ground, so V2 is ground. Basically, what's going to happen is we're going to have this whole op amp here. It's going to be basically gone. That op amp will not have any effect on V1. So what we can do is we can just not deal with that op amp. So let's only analyze, and we'll call this amplifier 1, amplifier 2, and amplifier 3. Let's only look at amplifier 1. Okay, so first question, do we have negative feedback? Let's see, so let's follow this line here. Oh, well, it's going back to the negative or the inverting input of our op amp. So yes, we do have negative feedback. We have a virtual short. Okay, V plus here is equal to V minus here. We also have no current. Perfect. Okay, is it inverting or non-inverting? Well, the input voltage is going towards the positive terminal of our op amp. Well, that looks like a non-inverting here. We have that right here. Okay. Okay, let's write that equation down. So for amplifier 1, V out, and we'll call this, we can even call this VA1, and we'll label it, actually, I guess it is labeled right here, VA1 right here. And we'll go with actually the same notation they have here, VA. So this is what we're finding, VA. Okay, so now, what is our R2 and R1? This isn't so clear, or maybe it is for some of you. What is R2? R2 is our feedback resistor. Okay, which one is our feedback resistor for A1? Well, this is our feedback resistor, R1. So we have VA is equal to what? Well, it would be VA over VN is equal to 1 plus R feedback, which is in our case is R1, divided by, well, now we have this, and R1 is connected to ground. Okay, remember before, what was V2? V2 was ground. R7 in this circuit is our R1 for the non-inverting amplifier of this circuit. I hope y'all can see that. I know it might be a little hard to see here because it's kind of in this weird configuration, but that's what's happening. R1 on the non-inverting amplifier over here is R7 for our circuit. So we have R1 plus R7, or 1 plus R1 over R7. That's what VA over VN is. So really we can write VA is equal to VN, or V1, sorry, times 1 plus R1 over R7. Okay, now what do we do with that? Well, that is our output for VA1, for our first amplifier. Now what we're going to do is we're going to look at this third amplifier, because we want V out. Okay, so how do we do this? Well, we know the voltage here. We ask ourselves 2 questions again. Do we have any negative feedback? Let's follow the op amp here. Okay, well, we go back to the negative terminal. We do have negative feedback. Cool. Now, that means we have a virtual short, and there's no input current. So V plus is equal to V minus. Now, is this inverting or non-inverting? Does this circuit here resemble more this or this? Another question you could ask is, where is our input voltage for the third amplifier at? Well, our input voltage is here. Let's follow here, and this goes to what? The negative terminal. That means we have an inverting amplifier. Okay, so let's write for A3, V out, and VO, we'll even write VO1 because we're using only V1, is equal to VA times what? Negative R feedback, which is R2 in this circuit here, over R1. Okay, let's see. Where's our feedback resistor? Well, this is our feedback resistor, R5. So let's write negative R5 divided by R1. Where is this resistor? Well, let's follow this here, and we go back, and it's right here, R3. I hope y'all could see that, how R3 in this case is R1 for this amplifier. So now we have Vout1. Vout1 is equal to VA, which we found to be V1 over 1 plus R4 over R7. And then that VA is multiplied by negative R5 over R7. So that's our equation for VA1. Perfect. This is only half of what we need to find. But do you notice, instead of writing, let's see, you're going to write this KVL, then you're going to write, you don't have to write, this node voltage. So you would have one equation, maybe two. Then you might have to write this one. And if you don't use superposition, you would have to write this one, maybe this one here. You would have to write a couple of node voltage equations. And sometimes it takes a toll on how much time you need to be able to put into these problems. And in the exam, you only have an average about, 15 minutes per problem. Now, the problems won't be set up like this. They might be something like this, but it shouldn't take you 15 minutes. It should take you maybe 10 minutes if you're doing this sort of equations. And if you can see, if you do this quick enough, you can do it in like 3-4 minutes. Now, that's the first part. Now, the second part here is let V1 equal 0. So now you're looking at the response of the output voltage when V2, or the amplifier 2, is in order. So again, we're letting V1 here equal 0. So we're letting this be 0. That means we have negative feedback A1. So this is ground, and this is ground now. Knowing that, what can we do? Well, we let V2 be something. That's just some input voltage. Okay, so now what do? Do we have negative feedback? Yes, we do. Is it inverting or non-inverting? Well, V2 is applied at the positive terminal, so it's non-inverting. So what we have here is V, and we'll call this VB because of right here, VB, is equal to V2 times 1 plus the feedback resistor, which is what? R2. If we can see again, the feedback loop is right here. R2 lies on the feedback loop, which is R2. So we have R2 over, now we want the resistor between the node that R2 is on, which is a V2 node, and that goes to ground, in our case R7. And remember, because V1 is 0, this becomes ground. So now you have R7 as this resistor, okay, VB. Now, what do we do here? Well, I mean, what are we doing now? We found the voltage here, VB, but now we want to find the Vout2 with respect to when V2 is the applied voltage. Okay, let's see here. Do we have negative feedback? We already know we do. Now we need to figure out, is it inverting or non-inverting? Well, the voltage is applied here, so we have some voltage, and it's being applied to the positive terminal. So we have a non-inverting again. But V in here is with respect to the voltage being directly applied to the positive input. But what is that, really? Well, we have VB here, and we have a resistor, and we have another resistor. So VC is the voltage we're looking for. So we're looking for plus and minus VC with respect to ground. So how do we find VC when we know the total voltage across this? We have two resistors, and we want to find the voltage of one resistor, not both. Well, that's a voltage divider. So what do we know now? V plus for the third amplifier is equal to VB times the resistor voltage we want to find, which is R6 over R6 plus R4. This one isn't in the typical way you would see an amplifier, a voltage divider, but it is a voltage divider. So we know what V plus 3 is. How does that help us? Well, now we know it's a non-inverting amplifier, and we can plug it straight into this equation because we know this is equal to V in, of course, V in of 3. So V out of 2 is equal to what? V in of 3 times 1 plus the feedback resistor. Feedback resistor, that's R5. Okay, so R5 and divided by non-inverting amplifier. What is R1 in our case? R1 is still R3. Remember, this one is ground also. We have no output of A1. So this would, in our case, would be R3 underneath. Then V out 2, and we'll put this in terms of V. It should be V2. Yes, V2 is equal to, what is V in 3? V in 3 is this here, VB times R6 over R6 plus R4. That is not in terms of V in 2, though. Well, VB, what is VB equal to? VB is equal to V2. That's what we need. So VB, which is V2 times 1 plus R2 over R7 times R6 over R6 plus R4 times 1 plus R5 over R3. There we go. Now, we don't want to find V out 2, though. We want to find V out total. So V out total, which we'll just say is V out, is equal to the addition of V out 1 and V out 2. That's what superposition is. We want to take the individual responses of each voltage and add them together to create a total voltage output. So what is V out 1? V out 1 is equal to V1 1 plus R4 over R7 times negative R5 over R7. I don't know why that... I might have like auto shapes on or something, because that was not looking like a 5. But then we add, we'll put this underneath, V2 1 plus R2 over R7. Hopefully I copied this correctly. R6 over R6 plus R4, which is our voltage divider, times 1 plus R5 over R3. And I will fix that here. This is R6. But there we go. That's V out in terms of V1 and V2. I do have auto shapes on. That's kind of annoying. Yeah, I do. Okay. So there is our equation in terms of V1, V2, and our, I guess, values, right? All right. So hopefully this made sense in trying to figure out what equations to use and how to notice these specific, I guess, like specific amplifier configurations. You always have to figure out, do we have negative feedback? And almost 100% we will. And is it inverting or non-inverting? You have to figure out where that input voltage is. Is it following up until the negative terminal or the positive terminal? And remember, this is very, very important. For the non-inverting, we have to find the voltage that is applied at the positive in terminal. So a lot of the time, what you're going to see, and I mean a lot of the time, you're going to see V in, or you'll see something like this almost every single problem. And this is the input terminal right here, and this is V in. But V in, we're not using that for the input or for our non-inverting amplifier equation. We have to use this value V plus. And a lot of the time, I always just put V plus is equal to, because it makes it a little easier to understand about which voltage I'm using. But you don't have to. You could use anything. You use VA, VN, or not VN, but VP. It doesn't matter. As long as you know what your voltage values are, or equations are in these cases. But they'll always use this. They'll always use this kind of voltage divider. And of course, if you have C, this becomes what 1 over j omega C1. And then what V plus would be equal to 1 over j omega C1 over 1 over j omega C1 plus R1. A lot of the time, not a lot of the time, but almost every single time, you'll want to simplify this. So this will become 1 over 1 plus j omega C1 R1. And now, if you've noticed, this here, this is a pole, right? You can rewrite this in terms of, or rewrite this 1 over 1 plus j omega divided by 1 over C1 R1. And now you have a pole at 1 over R1 C1. C1 R1, however. But that's your pole if you have a voltage divider. And of course, if you have like some sort of negative feedback. Oh yeah, and then you have like this resistor over here, right? And you connect it to ground. But yes, this is how you would solve it. In the phasor domain, works the exact same way. Now, we're getting close to 25 minutes. I kind of want to let y'all do this one, because this one's going to take a little too much time, and I want to make my videos a little less time. Yeah, I'll let y'all do this one. Just notice, again, first question, what do you ask? Negative feedback? And then 2, do we have inverting or non-inverting? Finally, in the case of differential inputs or differential amplifiers, difference amplifiers, if you ever have this kind of thing, let's say they give you this as VID. Let's say this is some sort of input, right? Something like this, I guess you could say. Actually, it doesn't even need to be that big. It could, yeah, it doesn't matter. Something like this, and let's say this is the negative side and this is the positive side. I'm just making this up on the fly, so let's say they give something like this, right? And this is just very arbitrary. This is a very simple. Let's just say this is R. No, let's say all of them are R1, whatever, right? Okay, so let's say we have negative feedback again. But instead of this weird, maybe not weird, but this, instead of having a voltage here and a voltage here, or let me do this here. Instead of having a voltage here and a voltage here, we have this differential input. I mean, how in the world do we do this? Because it's not certain non-inverting or inverting. We have difference between the two. So what we do first is, do we have negative feedback? First question. We do. So we have a virtual short. So the voltage here is equal to the voltage here. And remember, we have a voltage divider. What we can do first is, to make this a little easier to visualize, what you should do is you should draw a voltage source here. And we can call this VID. But what do we know about this voltage source? Well, we know that there's some input current, IN, right? And because we have a difference voltage source, we have this. This is still IN. Well, and what? We know this is IN still, since this is zero current. This is also zero current. Well, this is the current through here, IN. What does that tell you? Well, look at this. All of the currents are the same. You'll notice this a lot for difference amplifiers. Also, there's another little trick you can do here. What do we know about the voltage, or the potential difference across the inputs of the amplifiers when you have negative feedback? Well, there's no voltage difference. What can you do then? It might make it easy to write a KVL here. So let's write one really fast. So let's say this would be what? VID is equal to IN. And remember, IN is all the same, so you don't have to worry about it. IN times 1 over j omega C1, I'm moving to phasor, plus what's next? Well, if we're going to do a KVL, we can go across the terminals. We do not have to figure out the voltage across R1. Now, be careful. This does not mean there's current flowing through this virtual short. There's not. There's no input current going through here. We're using this as a loop because this is an open circuit there. This is sort of like an open circuit of 0 volts. But we can jump. Voltages can jump, currents cannot. So, what can we do then? What's the next resistor that feels that current? Well, that's this resistor. If we follow through here, I'll do this in green, I guess. If we follow through, we go through C1, we go across the virtual short, and we hit R1, and we're back to where we started. Perfect. So now we have plus R1. This is mostly all you need. But that's a very simple way to analyze your difference inputs, or differential amplifiers. This is important for homework 4, I think. That was homework 4 or 5. I think it was 5. This is important for homework 5 because I don't think he went over it very well in class, but this is kind of a good way to analyze these. Just to make sure you remember, because you do a KVL and go through that short, the virtual short, that does not mean current's flowing through there. That just means you can jump it because you're a voltage, not a current. So if you were to do a KCL at this point here, you do not put current going through this way because there's no current going through the input of the op amp. There's no current going through the short circuit or the virtual short you're creating because there's negative feedback. But this is what you would do. Okay. All right, hopefully that helped. And remember, make sure to do this problem if you want. It will help a lot. And if this helps y'all, this is called a voltage follower, where you have no feedback resistor. Well, why is that? Well, if you have this sort of thing, remember this is in non-inverting, so you have 1 plus RF over RN. RF is 0, so you just have a V in is equal to V out. That should help you with this question. All right, guys. Thank y'all for joining, and I hope this helped y'all, guys. because I've had people ask me like, how do you figure out, what equations to use, because they don't see it as clearly, and it really is just practice and taking the time to asking these questions and figuring out what's your feedback resistor and what's your R1 or whatever you want to think about it as. But hopefully this helped y'all, and yeah, I'll see y'all on the next one. Thank y'all.